Hello, Friday 5th of April 2024. Let's see if we can get started on problem 4. This reminded me of proposition 17, or actually 17a. So I wrote it up. These are zeros. And this is a matrix. And then we'll see how far we can write on proposition 17a. It's proportional to the g defined in the problem. So we need to compute if this is gamma, and if gamma mark is gamma 1 of n, what is actually alpha to minus first gamma 1 of n alpha intersected with gamma itself. So we work So we work modulo n, it's gamma 1 of n. That is, we have gamma is equivalent to 1, 0, 1, 0. This I might very well have done ahead. Let's just write A, B, C, D. So the first one multiplies the first row by by m. So it works on the column, the first column, sorry. And the next one operates on the first row. So that means that MC is actually Mn divides MC because n divides C. And we only take those where M divides B. So that means that this is a subset of gamma naught of Mn. And what did we need to prove? we needed to prove that when it's in M1, that is when n divides b, it's still equivalent to but that's a smaller group, so if it lies in this group, then of course it lies in this group as well. So that was the first step, thanks to proposition 17a. So what we need to show is that it transforms correctly. And that is g of gamma, still k, equals something times g itself. And that something, of course, should be chi mark of d. So we need to compute this. I'm confused here. Because this means that if gamma lies in gamma naught of level mn, then it should give itself but if we take any one, yeah, of course, this lies in gamma naught, but we don't hit all of gamma naught. That's the point. So we need to take any gamma in gamma naught. And then check what happens. And I think we should try to go backwards. I don't know why, that'll probably be clear later on. Oops, alpha only, it's only m, b divided by bm, c divided by m, d. You see, c divided by m is divisible by n. So it actually lies in gamma naught of n. And that means that f operated by alpha, gamma, alpha to minus first equals chi of b, chi of m. This is, of course, provided f lies in this space times f. F operated on A, that's what I called G. And then we operate on the left-hand side with alpha, or on both sides with alpha. And that's chi of b, chi of m, g. I wonder if that was what we needed to prove. That's not at all clear to me. That's actually very unclear. But we need to prove that this equals chi of b modulo m. That's what I need to prove. That's very unclear. If B is like unity, chi might be a multiply of n so that it vanishes. But this would still be the same. Nope. All right, that was what we could do for now. I'll go through it again and see if I find a mistake, and then hopefully I will find out how to handle this. Today is Sunday afternoon, and I have realized what my mistake was here. I happened to use the wrong entry of the matrix. One must use D, of course. And then the stuff that's going on here is that this chi works on this multiplicative group. But when we operate on these functions, it's a vector space, then we must have a guy operating on at Mn. So we just have oh, it's the multiplicative group. So we just have to map these into these. And the problem is, of course, that some will map to naught. So, well, never mind. That's an irrelevant detail. I always considered it to be Dedekind characters, so that we actually needed to define it a little more. But it's just that those that have common divisors with n maps to naught. So back to the next step. There's so much light that it's annoying me. I can hardly read the screen. We have mk of n chi and mk of mn chi mark, and they are essentially the same, or rather this one is this one is reducible because it comes from this by extension. And we have, of course, that gamma nn is a subset of gamma n, meaning that this guy is much larger. I hope that's what it states here. Yes. So we have an f in here, and it will also lie here, of course, but so will f of mz. I just wanted to say one thing. That's the point of using proposition 17a, because I did something that looked like the proof of it, is that proposition 3.8, that when we take any member of gamma itself and operate on the function, then it has the right series expansion. I don't need to verify that. Now, then on this guy we have Tn, and on this guy Tn mark, T mark of n operates so we have to show that they basically give the same result. And it commutes with putting m on it. So this is g of z. So in this space we have the modular points and in this one divided by mn. And we know that n is prime to n. And that means that those extensions of order n of this lattice, for which 1 divided by n is still exact of order minuscule n, then that will hold for 1 divided by mn as well. They proved that. My God, how much light we've got. In a way it's wonderful, but I know I look like shit on the picture, but never mind. They actually put an argument for that in I think it's the proof of proposition 17b, I'm not sure, but maybe we should look at it again. So we have some generator 1 divided by d, where 1 divided by n has exact order minuscule n, which of course means that d fails to divide n. Then dm will fail to divide mn. Nah, that's not right. D will fail to divide mn. The other one is right as well, and that means that we can use the same lattices, extension lattices. So that shows that that shows the first one. Let's make it blue. That shows this guy. The other one, that when we take G and do the same, then it's just mz instead of z. And then when we go around doing this, we get the same ones. And then we put mz instead of z. That makes no difference at all. So that's really, as far as I can see, quite trivial. So we can simply use the same extensions of the lattices of order n in both cases. All right, that solves, as far as I can see, problem 4a.